everyone. Here the question says a satellite moves around a planet in a circular orbit at a distance r from its center. The time period of the revolution. Here the time period we are speaking about the time period right here of the revolution of the satellite is t. If the same satellite is taken to an orbit of radius 4r around the same planet, the time period is going to be definitely changed, right? Because the radius is going to be changed, so the time period is definitely is going to be changed. Okay, so it can be solved using the Kepler's third Kepler's law. So first we have to understand about the Kepler's first law. So first law states that so always if this is a elliptical, okay, this is an elliptical orbit. Okay, in an elliptical orbit the planet or any the center the atom is going to be centered particle or mass is going to be placed right here. If it is a solar system, it is sun. If you talk about the satellite, it's planet, which is colored in the red color, is called the planet. Okay, it either one of the focus of the ellipse. We know that the focus of the ellipse, these are the two focus of the ellipse right here. Okay, any one of the focuses should be taken as planet. This is the first law of Kepler. So first law has been completed right here. The second law is nothing but, okay, so like this, so like, okay, sorry, this is not going to be like this. Okay, this is going to be like this. So these both are triangles. Okay, this is a triangle, this is a triangle. So the satellite which is going to be runs around this orbital, so this is going to be satellite. I will be just drawing a satellite in any other colors. Okay, I'm just using green color. This is satellite. Okay, this is satellite. Actually the satellite should be run around this elliptical orbit. Okay, so this is the important thing. So that the time period to travel from here to here, okay, to, okay, to cross this area per unit time is said to be constant. Okay, and not only this, and also this triangle. So to cross this triangle unit area of this triangle per unit time to cross this thing is going to be, this is area is going to be same for both things. This is Kepler's second law. So finally we have to look at the Kepler's third law, which is going to necessary for us right now. So Kepler's third law is nothing but, okay, so distance between, okay, this is the distance between, so from this point I am just taking from this point to the, okay, this is the distance between these two is, okay, or minimum. The radius, the distance between this planet and this satellite is going to be minimum at this point in the orbit. Okay, and this from here to right point this here is going to be r maximum. Okay, this is the, we are going to discuss about the third law. So this a, let us consider a is equal to r minimum plus r maximum, r minimum and r maximum divided by 2. Okay, a. So then the time period to travel, the square of time period is directly the cube of this distance, r minimum plus r maximum by 2. This is Kepler's third law. Okay, so to exactly we have to derive about this thing. So for that I am just taking mv square by r is the centripetal force. This is going to be the gravitational force. Capital M is nothing but, the capital M is the mass of this thing, okay, which is centrally located, and this mass small m, which is going to be written here, the small m here and here, is going to be the mass of this thing, this is capital M and this is small m. To differentiate I am just writing it like this, okay, by r square. Okay, we know that about these two things. Okay, this is centripetal force and this is the gravitational force. Gravitational force is going to be act as the centripetal force right here. Okay, and just I'm saying that that is a v square. So simply I can able to complete this equation. So v square is written here, right? V square is written here. So v is nothing but displacement by time. Here the displacement is going to be 2 pi r. 2 pi r is going to be the displacement by the time period. to cover this distance. So I'm just substituting this thing here, right here, so in this equation. So to substitute here, so before that I will be just cancelling this mass m in this equation, and the square, okay, and this r, okay. So the next equation can be written as this v, I'm just substituting the v also. So 4 pi square r square by time square, which is equal to G capital M divided by R, okay, because square has been cancelled right here. So from this equation you can able to say that, okay, okay, uh, S t square, which is going to be equal to, so t square is going to be equal to 4 pi square 4 pi square r cube by g m, okay, yes, okay. When this r is going reacting here, this r square r cube will be formed. So uh, t square is directly proportional to the cube of radius. So this is the third law which is going to be useful for us right now. Okay, time period, t is a time period. So for that, right now here, t square is directly proportional to the r cube, okay, according to the Kepler's third law. So at the first, the distance is going to be r and the time period is going to be t. In the first condition, so distance is going to be r and time period t square is equal to, in the first condition, this is in the first condition right now, so r cube. In the second condition, the same satellite is taken to an orbit, so the radius becomes 4r, so 4r cube, and this is the time period x we have to find right now here. So from this equation, so we can able to solve 64, okay. T square, which is okay, t square by, so x is equal to t square by r cube into, so 4 cube is 64, 4 cube is 64 r cube, 64 r cube, okay, right. I'm just cancelling this r cube, okay. So this is also is going to be square, actually this is also is going to be square, we have to find in the form of square only, okay, as per the rule. Square of this x is going to be the final answer as per the rule, okay, since we have to take the time period in the square, okay. That's the thing you have to understand here, right here. So the equation can be also written as, this is the initial by the final, so which is going to be equal to initial by final, okay. So normally this left hand side should be square as per this equation, there is this Kepler's third law, and this equation should be in the cubic value. So this is the thing, okay, you should understand this thing, okay. Now 64 times square is equal to x square. So taking square root on both sides, so this root and this t is get cancelled right now here. So this square will be cancelled, this is will be cancelled, this is cubic, so this is square root, actually square root means this is 8 8 are 64. So 8 8 are 64, 8 times t is going to be equal to the x, that is option A is the correct answer for this question. Thank you.